In the following, I'm going to discuss a proof, I'm going to give a proof of Euler's rotation theorem, which states that the arbitrary motion of a rigid body about a fixed point can be accomplished by rotation about a fixed axis through that point and an angle theta. To begin with, I'm going to specifically designate vectors and linear transformations with respect to any particular coordinate system. Then I'm going to discuss a few invariants with respect to change of bases. And then finally, I'm going to change the transformation matrix which describes the motion to an eigenvalue basis. Thank you. Hello, today I'm going to discuss change of basis systems for an arbitrary vector. To begin with, I'm going to assume an arbitrary basis E1, E2, and 3, and I'm going to define a second basis as linear combinations of E1, E2, and E3. And that's done as follows. This is F1 with respect to E is going to be F1, E1 plus F1, E in E2 direction to E2 plus F1, E3, E3, and so on for F2 with respect to E and F3 with respect to E. Now, having F1, F2, and F3, I could turn around and say these are my original basis vectors and define E1, E2, and E3 with respect to F. And I do that by solving these three equations for E1, E2, and E3 in terms of F1, F2, and F3. Then I get that E1 with respect to F is E1, F1, F1 plus E1, F in this direction F2, F, E1, F2, F2, and so on. Having done that, I now can say, for example, if I have an arbitrary vector A, and I have these two coordinate systems E and F, that A in terms of the E coordinate system is AE1, E1 plus AE2, E2 plus AE3, E3. Then if I would like to express A in terms of the F coordinate systems, what I can do is express E1, E2, and E3, E1, E2, and E3 in terms of the F coordinate system, and then E1, then I have A with respect to F is A21, E1 with respect to F plus A2, E2, AE2, E2 with respect to F plus AE3, E3 with respect to F, which I then can write A with respect to F is the matrix whose first column is E1 with respect to F, in other words, E1, F1, E1, F2, E1, F3. The second column is E2 with respect to F, in other words, the second column consists of E2, F1, E2, F2, E2, F3, and similarly for E3 with respect to F, and multiply that by A with respect to E. This is nothing but this equation in matrix form. Then I can write this with the symbol, with the matrix symbol E with respect to F, and then A with respect to F is E with respect to F times A with respect to E. On the other hand, if I start off with A in the F coordinate system, in other words, A with respect to F is this, then doing the same thing I did here but in reverse, then I can substitute for F1, F2, and F3 in terms of E1, E2, E3, and then I get that A with respect to E is, you can follow this when at your leisure, A with respect to E is the coordinate change of basis, is the change of basis matrix F with respect to E times A with respect to F. Then from these two equations, you get that E with respect to F times F with respect to E is equal to the identity matrix I. Now, if we look at the special case of right-hand orthogonal coordinate systems, by orthogonal I really mean orthonormal, but orthogonal is the three right angle unit vectors E and F. Then if we take, if with that basis, with those two bases, the change of basis matrix E with respect to F transpose times E with respect to F is equal to I. And You can see that by direct substitution of what E and F and E transpose and E with respect to F. E with respect to F, I'm going to just do it in two coordinates for simplicity. E1, I'm going to express as a row vector, and it has components E1.F1, E1.F2, and E2 with respect to F as a row vector has components E2.F1, E2.F2. Then E with respect to F has components E1 with respect to F, which is E1.F1, E1.F2, E2 with respect to F, which is E2.F1, E2.F2. Then if you multiply the rows and columns of these two vectors, you get this row times this row is E1.E1, which is 1. This row times that column is E1.E2, which is 0. E2.E1 is 0, and E2.E2 is 1. So you get that indeed E to the F transpose times E to the EF transpose times EF is equal to I. Finally, if you have more coordinate systems, this is general again. Suppose I'm given E1, E2, E3, totally arbitrary, and I define two other coordinate systems, F with respect to E and G with respect to E. Then A with respect to F is a change of basis vector E with respect to F times A with respect to E. A with respect to E is a change of basis vector G with respect to E times A with respect to G, which means A with respect to F, if I substitute this in here, A with respect to F is E with respect to F, G with respect to A with respect to G, which says that this E with respect to F times G with respect to E is G with respect to F. It just shows how to switch around between more than just two coordinate systems. Now I'm going to discuss the change of basis for a matrix of a linear transformation. Linear transformation, just to remind you, is a transformation from Rn to Rn such that T times alpha A plus beta B is equal to alpha times TA plus beta times TB. Now if I have an arbitrary vector with respect to the E-coordinate system, AE is AE1, E1, AE2, E2 plus AE3, E3, then TAE is equal to AE1, TE1 plus AE2, TE2 plus AE3, TE3, which can be written as the matrix product of the matrix which has for its first column TE1, its second column TE2, and the third column TE3. In other words, the columns of the matrix of the transformation matrix are the transformed basis vectors E1, E2, and E3, and that's multiplied by A with respect to E. And this is abbreviated as the transformation matrix T with respect to E times A with respect to E. T with respect to E is the matrix of transformation with respect to the E-coordinate system. Now we might ask ourselves, well, what does that matrix look like in a different coordinate system? So suppose I change to a G-coordinate system. Then the change of basis to T with respect to G can be derived as follows. B with respect to E is T with respect to E times A with respect to E in the E-coordinate system. Now, if I'm B with respect to E is G with respect to E times B with respect to G, all right, that's using this formula here for the transformation of basis, and that's equal to T with respect to E, G with respect to E times A with respect to E on this side is G with respect to E times A with respect to G. So I've just transformed B with respect to E and A with respect to E using the transformation of basis matrix to the G coordinate system. Then if I multiply this equation by the inverse of G over E, which is E over G, we had that before, then I get that B with respect to G is this term times A with respect to G, and this term here is T with respect to G. because b with respect to g is t with respect to g times a with respect to g, so that t with respect to g is e with respect to g, t with respect to e times g with respect to e. I forgot something. Well, I'm going to tack it on here. T with respect to e can also be written as f1 with respect to e, f2 with respect to e, and f3 with respect to e, where f1 with respect to e is te1, f2 with respect to e is same vector as te2, and f3 with respect to e is te3, in which case t with respect to e is simply the change of basis matrix F with respect to E, and you can write T A with respect to E is F with respect to E times A with respect to E. But again, now in this case, notice the location of the E's as opposed to the location of the E's in this in this formula here, which is the change of basis matrix for a change of basis matrix for a coordinate transformation. In this case, F with respect to E is a change of basis matrix for a transformation, for linear transformation. I don't remember whether I covered that before. If not, it doesn't matter because I just reviewed it. Then I can symbolize all these transformations by this little rectangle here, where if I start with A with respect to E, the transformation T with respect to E transforms A with respect to E to B with respect to E. Now, A with respect to E can be written in the G coordinate system as E with respect to change of basis matrix E with respect to G times A with respect to E, which gives A with respect to G. And B with respect to E can be changed to the G basis with the change of basis matrix G with respect to E to give B with respect to G, and A with respect to G, T, the transformation matrix T with respect to G acting on A with respect to G is B with respect to G, and T with respect to G, the transformation matrix in this coordinate system is given by this expression here. So that finishes. Get over the other side. Okay. That finishes the background on this change of basis system that I've presented. I would now like to discuss some invariants as a preparation for the proof of Euler's rotation theorem. Okay, so begin with the linear transformation preserves dot product. So I want to show that Tx dot Ty is equal to x dot y. All I have to do to show this, all I have to do is use the formula that AB transpose is equal to B transpose times A transpose, and I get that TE transpose times TE is equal to I, because the assumption was the original orthogonal linear transformation T with respect to E was orthogonal, which makes this I, and I get x, y. Next, the eigenvalues are invariant, and eigenvalues of a transformation, linear transformation, are invariant with any change of basis. So here I have the linear transform. I have Tx is equal to lambda x, and I'm going to show that with respect to the basis f, that the eigenvalue equation with respect to the basis E has the same value of lambda. To do that, I'm going to substitute for t with respect to f from here. This is this term, and then x with respect to f, which is this term, times this term, and that's equal to lambda x with respect to f, which is this term. Then f with respect to e with respect to f is equal to I for any bases e and f. That leaves e with respect to f here, and multiply f here. If I multiply by the f with respect to e on each side, they become I, and I'm left with Tx equal lambda in the e basis coordinate system, E-basis system. Now the trace of a linear transformation matrix is invariant with any change of basis. To show that, I'm going to start with the trace of t with respect to f is equal to the trace of t with respect to f as given by this formula here, which is the trace of this times this, which is the trace of b. The trace of ab is the trace of b times a. So this is, there's the b, there's a, and again we have the same formula coming out, f e e f is equal to I, and this becomes the trace of t with respect to e, which proves the trace of linear transformation matrix is invariant. Finally, I want to show that the orthogonality of a linear transformation matrix is invariant under an orthogonal change of basis, i.e. g with respect to e is orthogonal. So to do that, I want to show that a linear transformation matrix with respect to G transpose times the linear transformation matrix with respect to G is equal to I. And to do that, I substitute for T with respect to G from here into here and here to get this equation. And then I get this very long expression, which is actually quite simple. And what I do is I just utilize AB transpose is equal to B transpose times A transpose, and the fact that the original linear transformation matrix with respect to the basis E was orthogonal, so T with respect to E transpose and T with respect to E is equal to I. Now if I just work that all out, and it's just elementary algebra, I get that this T with respect to G transpose times T with respect to G is equal to I. And now I'm going to prove Euler's rotation theorem, which states that an arbitrary movement of a rigid body about a fixed point can be accomplished by a rotation about an axis through that fixed point. To begin with, I'm going to embed three unit vectors E1, E2, E3 orthogonal in the original system. And then after moving from the original position to the final position, E1, E2, and E3, E1 goes to F1, E2 to F2, and E3 to F3. Now, the transformation from E1 to F1, E2 to F2, and E3 to F3 defines a linear transformation T by T E1 equal F1, T E2 equal F2, T E3 equal F3, which has a transformation matrix, which defines the transformation matrix T with respect to E, equal F1 with respect to E, F2 with respect to E, F3 with respect to E, and that's equal to the change of basis matrix F with respect to E, which is orthogonal. And that's very important. Because T is orthogonal, dot products are invariant, and which means lengths and angles between lengths in the rigid body don't change. So T describes the motion of the rigid body. Now, first I'm going to determine the eigenvalue. I'll write the eigenvalue equation with respect to the coordinate system, which is Tx equal lambda x. Then I'll take the transpose of this to get this term. AB transpose is B transpose A transpose. If I multiply this term and this term together, this side times this side on the left, this side times this side on the left, then I get that the main thing to note is that TE transpose times TE is equal to I, because as we just showed, T is orthogonal. And then you're left with cancellation, and lambda squared equal 1 for a three-dimensional system means lambda is equal to plus or minus 1, and lambda is equal to e to the plus or minus I theta. And that comes from solution of the eigenvalue equation, which is cubic in this case. One root is lambda equal 1, and that leaves a quadratic with two imaginary roots. Okay, then, now this is the crux of the whole proof. I'm going to change to an eigenbasis. I'm going to let G1 G1E be the solution of this equation. G1E, the solution of Tx equal lambda for lambda equal 1. Then I'm going to add G2 and G3 to create a right-hand orthogonal coordinate system. Then I'm going to compute the transformation matrix in the G coordinate system defined by the eigenvector G and then G2 and G3. So T with respect to G is from the previous sections. T with respect to G is E with respect to G, T with respect to E times G with respect to E. And because G is orthogonal, E with respect to G is equal to G with respect to E transpose. Now why was G, oh yes, G is orthogonal. G is orthogonal by definition. Good, thought I had a problem there. It's all right. Now, I just as a review, I note that G we have change of basis matrices G with respect to E, E with respect to G. Their product is I, and E with respect to G transpose times E with respect to G is equal to I if E with respect to G is orthogonal, which it is. Right, now I can write this T with respect, at this point, now we come to the heart of the proof. It's just a matter of filling in the terms and interpreting them. So T with respect to G is G with E transpose, so that's G1 with respect to E as a column, as a row vector, G2 as a row vector, G3 as a row vector, which we multiply that times T with respect to E, then G with respect to E, G1 with respect to E, G2 with respect to E, G3 with respect to E, where these are column vectors. Now if I multiply this times this, the first term that I get, T times G1, because T is the transformation matrix in the G coordinate system, T times G, no, because by definition, Tg1 was equal to G1. I'm sorry, by definition, G1 was the eigenvector of the transformation. So T times G1 is G1. Then we're left with this times this and this times this. Then we multiply this term times this term. Then for the first column, we get G1 E row times G1 perpendicular, which is G1 dot G1 is equal to 1. Then we get G2 dot G1 is 0. G3 dot G1 is 0. And then we get the rest of these terms. For example, this term here is this times this. This term here is this times this. This term here is this times this. And it's standard matrix multiplication. Now we're finally going to look at this transformation matrix with respect to the eigenbasis G, and it has all the information that we need to draw our conclusion. To keep things simple, I'm going to express it without the E subscripts, which is this result over here, or this matrix over here. And I note that the orthogonality of T is invariant with respect to an orthogonal change of basis, which says that this column times this column is 0, which says that this term is 0. This column times this column is 0, which says that this term is 0. That, in turn, says that G1 is orthogonal to T, to the transform vector G2, and G1 is orthogonal to the transform vector G3. Now, I can show all these relationships in a diagram where I have G1 coming out of the board. Tg1 is equal to G1 because G1 is an eigenvector. Remember, Tg1 is equal to lambda G1. Lambda is 1. And then here's G2 and G3, orthogonal to G1, of course, by original definition. And here's Tg2 and Tg3, orthogonal to G1, because these terms are 0. Finally, I'm going to invoke the orthogonal, or the invariance of the orthogonality of G1, G2, and G3 under an orthogonal transformation, so that I can say Tg2 is orthogonal to t g3. So now all the orthogonality relations are included in this diagram here, and I can finally look at these four terms here, where this g2 dot tg2, g2 dot tg2 is the cosine of theta between these tg2 and tg2. g2 dot tg3 is the cosine of the g2 dot tg3, the cosine of the angle alpha. g3 dot tg2, g3 dot tg2 is the angle beta. Cosine is the cosine of the angle beta, and finally g3 dot tg3 is the angle gamma. Now, there are some very simple geometric relations between these angles, and they are as follows. The angle beta is 90 minus theta. The angle gamma is equal to theta, and the angle alpha is 90 plus gamma, which is 90 plus theta. Then if you take the cosines, as indicated in these terms, you finally wind up with the transformation matrix with respect to the eigenbasis B as being 1, 0, 0, 0 cosine theta minus sine theta, cosine theta. And that is the transformation matrix of a rotation through an angle theta about the eigenvector or the axis G1, the eigenvector G1, which proves Euler's rotation theorem. And finally, we note that the trace of t with respect to G and t with respect to E is invariant, so that 1 plus 2 cosine theta is the trace of t with respect to E, which we know by our definition of the E and F coordinate system. And we also have that the eigenvalues of t with respect to the G and E coordinate systems are invariant. And we can calculate the eigenvalues from here, and the eigenvalues are 1, and the solution of the quadratic from the the eigenvalues are 1 e to the plus or minus I theta, which is the solution of the eigenvalue equation, lambda minus 1 times these terms here, minus this minus lambda and this minus lambda. That's it. Thank you for your patience.